Hello everyone, thank you for coming to my talk. My name's Sam Upton and today I'll be talking about work that I've been undertaking with my supervisor Adam Pound on the second order gravitational self-force in a highly regular gauge. So first I want to give a brief recap of what the self-force is. It's a perturbative method to solving the two-body problem in general relativity that is particularly applicable when we have a small separation between our two objects and we have a high mass ratio between them. Essentially what we are doing is we say we have some exact metric that describes the big black hole, and then there are perturbations to it caused by the presence and motion of the small black hole. As we can see here, it's a power series in the mass ratio where m is the mass of the little m is the mass of the small black hole and big M is the mass of the big black hole. So we expand our metric as so, our exact metric as so. We also have an equation of motion dictating the motion of the small object, which is given by this. This at leading order is just the geodesic equation. And then at sub-leading orders, we have corrections, which we call the self-force. These forces can be split up into two terms, a conservative and a dissipative piece. And one of the things that is known is that to perform accurate tracking of the small object, we need both the full first order self-force and the dissipative part of the second order self-force. So, as I said, second order perturbation theory is crucial for LISA, for modelling EMRIs. And as I stated before, the parts of the second order self-force are just as important as the full first order self-force. Now the bulk of the work by the community so far has been at first order. One of the major hurdles at second order has been the strong divergences of on the small object's worldline. So generically, the second order singular field would go like m squared over r squared, where r is the distance to the small object's worldline. However, it was previously shown that there exists a highly regular gauge where the singular field goes like m squared over r. Only the leading order behavior was presented in that previous paper, but we have extended this to order r as required for numerical implementation. Now this less singular structure has a number of nice benefits. Firstly, any numerical implementation will be much quicker, as we don't have to deal with such strong divergences. But also, it allows us to rigorously define a second order stress energy tensor, which we would call the Detweiler stress energy tensor. So I briefly want to go over the principle of matched asymptotic expansions, which is key to understanding why we can eliminate this the most singular 1 over r squared part of the second order perturbation. So here we have G exact, which describes the full space-time containing the big black hole and the small black hole. But we can choose to expand it perturbatively, where we have G, which describes the big black hole, and then perturbations caused by the small black hole. Or we can expand around the small object. So we have the metric describing the small object, and then perturbations caused by the curvature or the presence of the big black hole. However, as these are both expansions of the same space-time, there must be some region in which they agree, which we call the buffer region. So one thing I really want to draw to your attention is that the most singular, the leading order behavior in R, in the perturbations and the background metric, are entirely dictated by the multipole structure of the small object. So if we can eliminate, if the small object does not have any of these multipole moments, we know we can eliminate them from our external perturbations. And in particular, I want to draw your attention to the epsilon squared over r squared term, which is the most singular part that we want to remove in HS2. So from matched asymptotic expansions that I discussed on the previous slide, generically the second order singular field, because I'm 1 over r squared, and this includes all previously used gauges in self-force, including the Lorentz gauge. However, we are specializing to a non-spinning spherically symmetric small object, which we can describe at a Schwarzschild line element in Eddington-Finkelstein coordinates as so. So we see straight away that this is linear in 1 over r. We have no terms proportional to 1 over r squared. In fact, with the light cone gauge condition, we eliminate this entire perturbation so that the second order singular field goes like r to the 0. However, it's not easy to implement numerical schemes in this gauge, as it constrains the regular field to go like r squared. This means that the regular field and its derivatives vanish on the world line. But we can find a practical gauge where the second order singular field goes like the first order regular field divided by r. Although this has a singular structure, it's still much better than any previously considered gauge. We call this practical gauge the highly regular gauge. Now, the transformation to the highly regular gauge is given by this. So we've split up our first, which is these two terms, and second order, which is these two terms, transformations, into irregular and singular pieces. So I should note that we impose that our gauge vector is smooth. So any Lie derivative of a smooth or regular quantity, we put in a new regular field in the highly regular gauge, and any Lie derivative of a singular quantity, we put into the new singular field in the highly regular gauge. So here we know HS2 goes like order r to the 0 in the light cone gauge, and now the Lie derivative of HS1 in the light cone gauge will go like 1 over r, which is what introduces our 1 over r behavior in the highly regular gauge. So to find the form of the gauge vector, we expand this equation in powers of 1 over r and then match at each order. I should say here that this regular field is undetermined but can be fixed using some preferred numerical scheme. We solve for the gauge vector as functions of the regular field. And we only impose two gauge conditions, that are that the gauge vector is smooth and that the world line position is preserved. So the spatial part of the gauge vector is 0 when evaluated on the world line. This ensures that we do not introduce any mass dipole moments into our expressions. And we need to go to order r cubed in the gauge vector. So that's just a process of matching order by order. With our gauge vector found, we can perform the gauge transformation to the highly regular gauge as so. So full expressions are unfortunately prohibitively long to include here, but they will be available in an upcoming paper. One thing that needs to be done is that it needs to be made covariant. They're only available in Fermi-Walker coordinates at the moment, so they would need to be made covariant using the techniques in this paper. We then can use the singular field as an input for some numerical schemes, such as the puncture scheme, where we solve these coupled sets of equations to determine the evolution of our system. So this less singular behavior also allows us to define things distributionally in the highly regular gauge as well. So generically, d2g has this form. It's a perturbation times a second derivative of the perturbation plus a derivative of the perturbation times a derivative of the perturbation. So that because HS1 goes like 1 over r, we can see straight away from order counting that d2g will go like 1 over r to the 4. However, we can choose to split up our HS2 in the highly regular gauge into two quantities. HSR, which is the singular m term, times a regular HR term, and an HSS, which is singular times singular, which goes like m squared over r to the 0. Therefore, we know by order counting in m that the source for dg HSS must be d2g HS1. But HSS goes like r to the 0, and because we can think of dg as just being two derivatives applied to something, we know that this constrains d2g HS1 to go like 1 over r squared. And this is an integrable function. It's valid distributionally across the entire space. So we have dealt with the most singular part that appeared in previous gauges. Also, we know, again by order counting, that the source for DGHSR, this term here, these terms proportional to these terms, must be D2G HR1 HS1, which we can define. So this goes like 1 over R cubed, which is not, which on its own would not be valid as a distribution. However, we can define it as a linear operator Q acting on HS1. Now, from distribution theory, we know that a linear operator acting on an integrable function is still valid as a distribution. So these terms are all valid as distributions. So off the world line, our second order Einstein field equations have this form. However, we know that all these terms are valid as distributions, and so we can extend to the world line. In fact, the regular fields are nice and smooth everywhere, so they pose no problems as well. Therefore, we can say that for all R, our Einstein field equations have some stress energy tensor as their source. So how can we know that it's valid to talk about a second order stress energy tensor in a highly regular gauge. So how do we find it? Well, we express it in terms of a transformation from the light cone gauge. So T2 in the light cone gauge is 0. That's something that we can calculate. It's no trouble at all. And we also have a gauge transformation, our Lie derivative applied to T1. So T1 is invariant under gauge transformation. So T1 is the same in all gauges. So we calculate that, so this quantity has already been calculated in terms of the gauge vector in this paper. So what we've done is we've taken our gauge vector to transform to the highly regular gauge, and we've substituted in the value for the gauge vector into this quantity here, and now we can express T2 in terms of the regular field of the highly regular gauge, which is just this nice simple expression here. In fact, the total T, the sum of T1 and T2, is nothing more than the stress energy tensor of a particle moving in an effective spacetime. So the effective spacetime is given by the background metric plus the regular fields. This confirms the conjecture made by Detweiler in this paper. And we have also extended this to the Lorentz gauge, so this the T2 that we found is valid in the Lorentz gauge as well, but there is a lot of subtlety going on there, and we're not entirely sure how useful this will be. So, what have we discussed today? Well, I've demonstrated how strong singularities near the small object can be alleviated using the highly regular gauge. I've discussed how the highly regular gauge can be used in a numerical scheme, such as a puncture scheme, to calculate the regular field and the equation of motion of the system. Also, one thing I haven't discussed, but is worth mentioning, is that the highly regular gauge opens up avenues to mode sum regularisation and Green's function methods for solving the dynamics of the system if we wanted to avoid using a puncture scheme. And finally, we've rigorously defined the Detweiler stress energy tensor, which is equivalent to that of a point particle moving in the effective spacetime G plus HR. So thank you very much for listening to my talk. Thank you very much.